Hello. Hello.
Hi, sir.
Hi. Um, we'll do both the chapters. Okay.
Okay.
Energy and momentum. So let's start with conservation of energy. Whatever doubts are there in the work for energy chapter.
Yeah. I didn't do the exercise. I did the workout example.
Okay. Question number.
9.
Okay. So there's a uniform chain of length L, mass M overhangs a smooth table with two-thirds lying on the table. Find the kinetic energy of the chain as it completely slips off the table. Okay. There is a table, there is a smooth chain. Two-thirds of it is on the table, the mass M, length L for the whole chain, right?
Yeah.
Now, it is a smooth, frictionless table, smooth, frictionless table, and it will slide down because this is being pulled down by gravity, right?
Yeah.
This portion doesn't feel a net force, it feels gravity, but there is normal force to support it, right?
Yeah.
So, this portion is being pulled down. Now, when it completely slips off, it will be in this situation, right?
Yeah.
You have to find kinetic energy at this instant when it completely slips off. So, fine. So, if you have read the theory, then you will know that there is work energy theorem, right?
Yeah.
Work energy theorem is the most important thing in the chapter, and the way you apply it is work done by all forces, work done by all forces is equal to change in kinetic energy of the system, right?
Yeah.
So you can list out all the forces and see how much work they do while the body goes from this initial state to this final state. So let's take the chain as a system and think about what are the works that are done on it, right?
Yeah.
So work could be done by gravity. There is no
Yeah.
friction, otherwise friction could have done some work.
Hmm.
Normal force doesn't do any work because normal force is perpendicular
Yeah.
and motion is in this way.
Hmm.
So work is force dot displacement. So force and displacement have a 90-degree angle, right?
Yeah.
So actually there is only one force that is doing work, that is work done by gravity. So work done by gravity is equal to change in kinetic energy, initial kinetic energy. So it is final minus initial. The final kinetic energy is what is being asked, and
Hmm.
initial was zero, right?
Yeah.
So you have to find the work done by gravity. That's all, right?
Yeah.
Now, now in this chapter again, there is the idea of conservative and non-conservative forces, right?
Yeah.
Conservative forces are those in which the work done does not depend on the path taken, right?
Yeah.
The work done depends only on initial pace, initial state, and final state, right?
Hmm.
So gravity is a conservative force,
Yeah.
and for all conservative forces, you can technically define a potential energy. So potential energy makes sense only for conservative forces because if your work done on going from this point to this point, suppose it had depended on the path, right?
Hmm.
This is path one, this is path two, right?
Yeah.
And they could you could make infinite different paths, right, to go to that point.
Yeah.
If the force was non-conservative, that means the work done depends on the path. Then
Hmm.
if someone did some work and brought it to this point, right?
Yeah.
This was work done in path one, right? If you did work
Hmm.
on A and brought it to point B through path 1, that was work done in path 1, then the work that you did will show up as the potential energy of B at this point, right?
Yeah.
Okay, so that would have been the value of potential energy at B, correct? Now, if you had taken a different path and come there, then the work would have been different if it was non-conservative force, right?
Yeah.
Then potential energy at the same point would have a different value, right? And similarly, infinite such paths are possible. So at any one point, you cannot even say what the potential energy is, right?
Yeah. Okay.
Are you understanding? There
Yeah.
are infinite different values possible of potential energy if it is a non-conservative force, right? However, if the paths didn't matter and if work done from here to here only depended on this point and this point, right?
Yeah.
Then you could assign a specific value of potential energy at this point without any confusion, right? So
Yeah.
only for conservative forces you can define a potential energy. And
Yeah.
we have the relation that work done by conservative force will be negative of the change in potential energy, okay, due to
Yeah.
that force. Because change in potential energy is equal to work done on that particle, right? Like, so suppose I am pulling a bucket of water and I'm bringing it to the top of a well, right? So I put the force and lifted the bucket, right?
Yeah.
So I did positive work and brought the bucket up, right?
Hmm.
So because of me doing all this, finally the bucket of water, when it is on the top of the well, it has more potential energy as a result of that, right?
Yeah. Okay. Yeah.
So work done by me is equal to the change in potential energy of the bucket of water, right?
Yeah.
However, at the same instance, think about what did gravity do on the bucket of water. Gravity did negative work, right?
Yeah.
Because gravity was pulling it down, but the displacement was up. Right?
Yeah.
So what we have basically is work done by external agent will be negative of the work done by gravity, right?
Yeah.
And this external
Okay.
agent work done is equal to change in potential energy of the body, right?
Yeah.
So,
Okay.
so we have the relation that work done by gravity is negative of change in potential energy, right? Due to gravity, correct? Are you understanding?
Yeah.
So all you have to do here is negative of change in potential energy is equal to kinetic energy, right? Final, right? Kinetic energy final, correct?
Yeah. Okay. Yeah.
So negative of change in potential energy is basically U initial minus U final is equal to kinetic energy final, right? So what you have to do finally now is find the initial potential energy, find the final potential energy, right?
Okay. Yeah.
Now this question can be done in multiple part, two ways at least. What we can do is, this is the situation, this is the situation, and initial potential energy. Let's try to find out, right? What we can take is that the potential energy at a specific level can be thought of as zero. We can choose whatever level we want. Let's choose this table as the level of zero.
Yeah.
The reason for that is that what we care about is the change in potential energy, not the absolute value. Okay. Ultimately, what matters is change in potential energy. So you can choose any origin or any level where the
Wait,
potential
so
energy.
there's nothing like absolute potential energy, it's only relative?
There is, I mean, there is nothing like absolute potential. There is something like absolute potential energy, but it depends on what origin you choose, right?
Okay.
I mean, for each origin that you choose, the absolute value will be different.
Okay.
Ultimately, what matters in any real problem will be the change in potential energy from initial to final. So it doesn't matter really where you choose your origin, except in some
Okay. Yeah.
special
Change will be the same.
cases. In some special cases, it will matter, but we'll see some cases in electrostatics where it matters that you choose your potential energy zero where, right?
Okay. Yeah.
But most of the time that doesn't matter, and what we will be dealing with is always a change and not the real value.
Okay.
So that we can take this as the origin. And if this is the origin, this entire portion is at zero potential energy, and this is the
Yeah.
portion at some negative potential energy, because this is y and x, right?
Yeah.
So this height is negative, right? So one way to do it is to use a center of mass concepts and know that if there is a uniform length L, and
Hmm.
the center of mass will be obviously at its midpoint, right?
Yeah.
So instead of this, you can think of it as a particle at this length, right?
Hmm.
Now this length was L by 3, so the particle is going to be at L by 6 depth, right?
Yeah.
So what is the mass here? Mass is m by 3, right?
Yeah.
Because total mass was m, so mass is m by 3 here. So particle of mass m by 3 is at depth of L by 6, right?
Yeah.
So potential energy would be mgh, and it becomes negative mgl by 18, right?
Yeah.
Now potential energy final. In the final situation, you have the whole thing like this.
Yeah.
So if you think about it, the particle is at depth of L by 2, right?
Yeah.
And the mass in this case is capital M, right? So
Yeah.
potential energy final is equal to minus mgl by 2, right?
Yeah.
So ui minus uf will become mgl by 2 minus mgl by 18. So that will become 8 by 18. So 4 by 9, right?
Yeah.
4 by 9 mgl is equal to the kinetic energy final, right?
Okay. Yeah.
So that is easy because we have taken center of mass, and we
Hmm.
have thought of the whole chain as the midpoint point, right?
Yeah.
Having that mass. However, you can also solve it in a more general way. Like if the chain was not uniform, you will not know where the center of mass is, right?
Yeah.
If the mass of the chain was unevenly distributed, then you would not know where the center of mass is, correct?
Hmm.
So in general, the way you should solve it also is this. And let's say this is the situation. Let's find the initial potential energy. So what we will take is a tiny mass dm at a depth of x, let's say, right?
Okay.
This is a tiny mass dm. It is there in the length of dx length, right? This length
Yeah.
is dx. So let's find the potential energy of this tiny mass. So it is called du will be minus dm g and its depth, right? Depth of
X.
this
Yeah.
mass, so x, right? And
Yeah.
we know how to write dm in terms of dx, because dm will be equal to capital M by L into dx, right?
Yeah.
Mass per unit length into its length, right?
Hmm.
So you'll have du is equal to minus capital M g by L x dx, right?
Yeah.
This is the potential energy of my tiny element.
Hmm.
However, what we have to do is add up the potential energies of all such elements, right?
Yeah.
So when you do integration of du to add up all the potential energies, you would do integration in such a way that it covers the entire hanging portion, right?
Yeah.
So x will vary from 0 to L by 3 in this case, right?
Yeah.
In the other case, the same integral will come, but x will vary from 0 to L,
Yeah.
correct?
Yeah.
In the final potential energy case, right?
Hmm.
So in this case, it will be minus mg by L, x square by 2, so L square by 9, right?
Yeah.
So minus mgl by 9 is x square by 2, so 9 into 2, right? 18. So minus mgl by 18 is coming,
Yeah.
and here it will be mg by L and L square by 2, right?
Yeah.
So mgl by 2 is coming here.
Okay.
So it's the same calculations. This is negative also. Same calculation, same values will come, right?
Hmm.
And you will get the 4 by 9 mgl answer of kinetic energy.
Okay.
So the important thing to note here is that you have to apply work energy theorem. So work done by gravity will be equal to the change in kinetic energy. There is no other work that is being done.
Yeah.
So work done by gravity to calculate you should use the idea that gravity is conservative, so it will be equal to negative of the potential energy change due to gravity,
Yeah.
right?
Okay.
So then this is done.
Yeah.
What
Uh,
else
the,
is there?
the 10th one also I didn't get.
Okay. uh a block of mass m pushed against a wall. Okay, spring constant k is fixed at one end. Pushed against a wall against a spring or spring constant fixed at one end. Block can slide on a frictionless table as shown in the figure. The natural length of the spring is L naught and it is compressed to half its natural length when the block is released. Find the velocity of the block as a function of its distance from the wall. Okay. This is, let's say, natural length L naught, and in it is compressed in such a way that it is at half its natural length right now.
Yeah.
Okay, and then it is released. Okay, then you leave it and it can go this side, right?
Hmm.
Now this distance is called x, right? The distance from the wall, right? You have to
Wait, I
find,
didn't exactly get what X is.
it has been given in the figure. See the figure
Uh,
8W6.
okay.
Find the velocity of the block as a function of its distance from the wall.
Okay, wait. So the spring is not connected to the block?
It is connected.
Oh,
It wait 1 second. It is pushed against a spring. No, it is not connected.
oh,
It is not connected. It is just pushed on against the spring and left.
okay.
After a point, it will be pushed back, right?
Yeah.
And eventually it might get free,
Hmm.
right?
Yeah.
And you have to find velocity of the block as a function of its distance x from the wall. Velocity as a function of x, distance from the wall. So, okay. Spring constant is k. Spring constant is k. Block can slide. Okay. On a frictionless table. Spring constant is k. Fine. So think about what happens as it moves this side, right? Uh, it moves this side because uh, initially the spring is compressed, right?
Hmm.
Spring is compressed and it exerts a force of KL by 2, KL naught by 2 on the block at the initial moment. Initial moment, why does it exert this much force? Because it is compressed by what amount?
L by 2. I mean, L not by.
L naught by 2 is the compression initial. So always spring force will be equal to K times either the extension or the compression, right?
Hmm.
You have to always calculate it from the mean position. So how much extension and how much compression. So notice that if it moves a little distance further, the spring force is now different, right?
Yeah.
Because now the compression is slightly lesser than L by 2, right?
Hmm.
Okay. So eventually it will reach the mean position, right?
Yeah.
The same position as above, right? So
Hmm.
that at that moment, spring force becomes zero. Spring force is zero now, right?
Okay. Yeah.
So you can find the velocity that it acquires here, right?
Yeah.
So let's take, however, we have to find velocity as a function of x. So what happens after that? Let's think about what happens after it crosses this boundary, right?
Hmm.
After it crosses, velocity will be constant, no?
Yeah.
Because then the spring will not be extended anymore, right?
Hmm.
Spring doesn't want to extend any further, right?
Yeah.
So it gives this velocity, it gives this push to it, and then it stops here and body goes away freely, right?
Yeah.
So technically velocity remains constant beyond this point because no more force acts on it, right?
Hmm.
So that tells us the function will become a constant function later, right?
Okay.
When x is equal to L, beyond L, it is a constant function, right? Velocity,
Okay.
correct?
Yeah.
So we only have to find the variation as it goes from here to here, right?
Hmm.
Okay, that is not difficult. So let's think about this distance being x, right?
Yeah.
Right. Obviously, x is greater than L naught by 2 and is less than this,
Yeah.
right? This is the situation. So work done by spring force. Is there any other force doing work? Gravity cannot do work in this case.
Yeah.
Normal force cannot do work because no other, it's in perpendicular, right?
Yeah.
It's perpendicular to the direction of motion. So work done by spring is change in kinetic energy, and change in kinetic energy is equal to kinetic energy final, which is what we need to find at this moment,
Hmm.
minus initial, which was starting point, which was 0.
Yeah.
So work done by spring is equal to kinetic energy final. Work done by spring force is also conservative, so that will also be minus del u due to spring, right?
Okay. Yeah.
So u initial minus u final, and this is spring potential, right?
Yeah.
Is equal to kinetic energy final. And u initial is half k L naught by 2 whole square, right?
Yeah.
Half kx square is the spring potential energy
Hmm.
minus u final. Now, if the total distance from here is x, right?
Yeah.
X here, then what is the compression right now? It is L naught minus x, no?
Yeah.
Compression is L naught minus x, are you sure?
Yeah, it is right.
Yeah, so total L would have been the length, but right now length is x, right?
Yeah.
So L naught minus x is compression. So potential energy at this moment due to spring is half k L naught minus x whole square, right?
Yeah.
That is equal to half mv square, correct?
Yeah.
So half cancels, and you will get an expression for v square. V square will be equal to k by m L naught square by 4 minus L naught minus x whole square, right?
Yeah.
Correct. So this makes sense, yeah. L naught minus x, correct. So I will just need some space here. So velocity is coming out to be root k by m L naught by 2 minus this. Let's simplify it a little bit. Root of L naught by 2 plus L naught minus x. So 3 L naught by 2 minus x multiplied by L naught by 2 minus L naught plus x, right? So x minus L naught by 2, right? This is the expression for velocity. However, this expression is valid only when x is between L naught by 2 to L, right?
Yeah.
When x is greater than L naught, right?
Hmm.
X is greater than L naught. So what was the speed at this moment? Let's put x is equal to L naught in this equation,
Yeah.
right? So it will become, or in this equation to be simpler, x is equal to L naught, this term disappears, right?
Oh,
So
yeah.
half k L naught square by 4 is equal to half mv square. So half cancels, k L naught square by 4 by m. So k by m L naught square by 4 is equal to v square. So
Hmm.
v is equal to root k by m L naught by 2.
Yeah.
Root k by m L naught by 2 is the v for this portion, and this is the variable v for this portion,
Okay.
right? So basically the velocity will be changing, and it will depend on, it will continue with this velocity afterwards, no, it will be
Yeah.
free, right? So this is
So it
the,
only varies from like L naught by 2 to x, I mean to L naught, and then it stays the same.
It will be increasing as it goes this side, no?
Yeah.
Because there is a force in that direction that causes some acceleration.
Hmm.
The
Yeah.
value of the acceleration is decreasing, but as long as it is there, some acceleration is there, velocity will be increasing. So
Okay.
velocity goes up from 0 to this value. This is
Hmm.
the value in this region, and eventually it reaches this point when the spring is completely at the natural length, after which no force acts and the body goes ahead and the spring stays as it is, right?
Yeah.
So this is the question.
Okay. And 14.
Okay. 14th one. Okay. So 14th one is a heavy particle is suspended by a string of length L. The particle is given a horizontal velocity. The string becomes slack at some angle and particle proceeds on a parabola. Find the value of V naught if the particle passes through the point of suspension. So it's like this. It is given some velocity. It goes like this till here, let's say, and here the string becomes slack. String becomes slack means the tension becomes
Tension is 0.
0, right?
Yeah.
After which particle proceeds in a parabola and passes through this point. So this is V naught. So you have to basically find V naught so that it passes through the parabola, right?
Yeah.
Passes through the origin, the suspension point, right?
Hmm.
Okay. So let's say this angle at which the string becomes slack is theta, right?
Yeah.
If this angle is theta, think about how you would have written the equation of motion at this point, or for Newton's laws of motion at this point. So you would have drawn a free body diagram. This should have been the tension. This would have been the mg, right?
Hmm.
And it would have some velocity here, v, correct?
Yeah.
So if you notice, uh, if it is going in a circle with velocity v, the acceleration towards the center is v square by capital R, right?
Yeah.
So R and all has been given length L. Yeah. So V square by L in this case, right? This is length L, right?
Yeah.
So draw the force components. So mg cos theta is like this,
Hmm.
right? Mg cos theta is this way because this is theta, and
Yeah.
mg sin theta is like this, right? So technically, one equation becomes T plus mg cos theta is the force towards the center, right?
Hmm.
And that should be equal to mv square by L, correct?
Yeah.
However, we know that string is becoming slack at this particular angle, right? That
Okay. So D.
means mg cos theta is equal to this, right? And t has
Yeah.
become 0, right?
Yeah.
So we have mg cos theta is equal to mv square by L. So that means basically v square is equal to gl cos theta, right?
Yeah.
This is my v square. This is the velocity at this point, right? Now,
Yeah.
energy conservation from here to here, right? Here to here, or work energy theorem would give us work done by gravity plus work done by string or tension, which is 0.
Hmm.
So, is equal to change in kinetic energy, right?
Yeah.
So, work done by tension is 0 because throughout tension is perpendicular to the velocity, right?
Hmm.
Work done by gravity from here to here would be negative because gravity is down and it is moving up, right?
Yeah.
So it will be minus mg whatever height it has gone up, right?
Okay.
So minus mg, this height will be L into,
So, 1
if
plus cos theta.
this is theta, L cos theta is this much, right?
Yeah.
Correct. L cos theta, so L into 1 plus cos theta is equal to change in kinetic energy, correct?
Yeah.
So you will get an equation here. Final kinetic energy is equal to half mv square, and v square is this, right?
Yeah.
Half mv square, and v square is mg L cos theta. right?
Hmm.
And minus initial kinetic energy is half m v naught square, right?
Yeah.
So therefore, what you get is half m v naught square is equal to this plus this, right? So mgl cos theta by 2 plus this, right? So mgl
Hmm.
common, it is cos theta
Okay.
by 2 plus cos theta. So 3 by 2 cos theta plus 1, right?
Yeah.
That is what it is, hopefully. Yeah. mgl common cos theta by 2 plus cos theta plus 1, right? So this is half m v naught square is equal to this, right?
Hmm.
Now, uh, let's think. Uh, what you need is, you know, your velocity and all now, right? So you can cancel the m. You can say v naught square is equal to 2gl. So gl into 3 cos theta plus 2, right?
Yeah.
You know your velocity initial for which this has happened, right?
Hmm.
Now, if you have to pass through the origin, right? Basically, what is happening is after this point, the string doesn't influence the particle, right?
I didn't
After
really
this,
understand.
after this point, the string is slack, right? It doesn't
Okay.
actually,
Yeah.
it doesn't give any force.
Hmm.
So after this point, it becomes parabolic motion
Hmm.
because of the influence of gravity,
Yeah.
right? So from here, you are launching a projectile and you have to pass through this point, right?
Okay. Yeah.
And this point is at a distance of L cos theta is this one, and L sine theta is this one, right?
Hmm.
You have to make it pass through this point, right?
Yeah.
So, okay. So if, and your velocity is in this direction. So if you draw a horizontal line like this angle is 90 minus theta,
Hmm.
right? And velocity is like this, so that angle is theta, right?
Yeah.
You're basically projecting it at an angle theta with velocity v, right? And hoping that it passes through this, right? You
Hmm.
know that it passes through this.
Yeah.
Okay. So let's say it passes through this at time t, right?
Hmm.
Time t. So I will just rub off and get some space here. Uh, so you have launched a particle like this at an angle theta with a velocity v, and it has to pass through a particular point here,
Hmm.
which is at a depth of L cos theta and a distance of L sine theta,
Yeah.
right? Okay. So horizontal velocity is v cos theta and vertical velocity is v sine theta, right?
Hmm.
Horizontal displacement should be L sine theta, right?
Yeah.
So in time t, it is going v cos theta into t should be equal to L sine theta, right?
Yeah.
And y vertical displacement is minus L cos theta, right? From this
Okay.
point,
Absolutely.
vertical displacement is down, right? So
Hmm.
minus L cos theta s is equal to ut. So v sine theta t, v sine theta t minus half g t square, right?
Yeah.
Okay. Instead of t, I will put this L by v tan theta, right? T is
Okay.
equal to L by v tan theta, right?
Yeah.
So I get minus L cos theta is equal to v sine theta into L by v tan theta minus half g t square. T square is L square by v square tan square theta, right?
Hmm.
Okay. This is my relation right now. V cancels, and v square I can put as gl cos theta here, right? You
Okay,
get
yeah.
minus L cos theta is equal to L sine theta into tan. So L sine square theta by cos theta minus, instead of v square I'll put GL cos theta. G will cancel, L will cancel. This becomes half L. Half L tan square theta by cos theta, right?
Okay, yeah.
Tan square is sine square by cos square, right?
Yeah.
And okay, so first I will just, okay, so L cancels from everything, right? L cancels from everything and multiply by cos, so it becomes minus cos square theta is equal to sine square theta minus half tan square theta, right?
Yeah.
And add the sine square theta this side, so it becomes, or subtract it this side, so it becomes minus 1, right?
Hmm.
Minus 1 is equal to minus half tan square theta, right? So tan
Yeah.
square theta is equal to 2, right?
Hmm.
Tan square theta is equal to 2. That means secant square theta is equal to 1 plus tan square theta is secant square theta, no?
Yeah.
Is 3, right?
Yeah.
So cos sec theta is root 3. So cos theta is 1 by root 3, right?
Yeah.
So V naught square is going to be 1 by root 3 into this, right? So 2 plus
Okay.
root 3 into GL, right? V naught square should be 2 plus root 3 into GL and root of that, right?
Yeah.
You understand? I found my V naught square because I
Okay.
found my cos theta, right?
Hmm. Okay, yeah, I got it.
So what are we doing? First, we have done the conditions on, we got this condition first. This condition we got by saying T plus mg cos theta is equal to mv square by L, right?
Hmm.
And
Yeah.
T is 0. Then because we got V square by conservation of energy from, or work energy theorem from this point to this point, I got this relation. This is my relation for V naught square, right?
Hmm.
V naught square is what was asked, but V
Yeah.
naught square has come in terms of the cos theta, right?
Hmm.
Since it came in terms of cos theta, I need to find the value of cos theta somehow, right?
Okay, yeah.
That's why they have given the additional information that it passes through the suspension point, right?
Hmm.
How did I find my cos theta? I thought about this being a projectile. After the string becomes slack, its motion is not affected by the string, right?
Yeah.
It is just basically going as if it's a free moving particle, right?
Hmm.
So then we know this information that it passes through this point. So this distance, it goes through this point, right?
Yeah.
We said, let's say it goes through the point at some time t, right?
Hmm.
So that distance should be equal to horizontal velocity into time, right?
Yeah.
And the vertical distance we put s is equal to ut minus half at square, right?
Hmm.
Eventually, after simplifying, you get the solution for tan square theta is 2, you get.
Yeah.
So tan theta basically is root 2. Perpendicular by base is root 2. So perpendicular is root 2, base is 1. So cos theta will be 1 by root 3,
Yeah.
right? So then you found your cos theta, correct?
Okay. Yeah. Got it.
Uh, okay. What else?
Okay, I had doubts on the next one.
Okay, conservation of momentum exercise, right?
Yeah. 38. Okay, we haven't asked him before. 19.
19th one, think about it. Tell me what is the doubt. 19th one, there is a man who is falling, and after he has fallen a certain height, he realizes that he was going to fall on the ground, right?
Hmm.
After he has fallen a certain height, uh, how much is that height? Uh, his height is at h.
Yeah.
Right now, his ground, from the ground, the height is h. Total height was capital H.
Hmm.
When he is at this point, he realizes he's going to fall on the ground, so he needs to land in the lake.
Yeah.
and he throws his briefcase towards this side with some velocity, right?
Hmm.
Hoping that he will get a backward velocity such that he, because he threw it midair right now, the center of mass will keep moving in the same with the same velocity.
Yeah.
In the horizontal direction, conservation of momentum will be there, right?
Hmm.
In
Yeah.
vertical direction, there is a gravity force, but in horizontal direction, there is no such force. So
Yeah.
if you throw something like this, he will acquire a velocity in this direction, right?
Hmm.
If he acquires a velocity in this direction, all you have to ensure is that he ends up here.
Yeah.
So this is doable. Try and do it.
Okay.
You should know this velocity, how much he will get if he throws it at v, right?
Yeah, we can use conservation of momentum and find it.
So that will simply be mv by m plus m, right?
Yeah.
1 second. No, not that.
Wait, I'll try
mv
and
by capital M, right?
okay, yeah, because the bag is not a part of him.
So he has thrown it. So let's say total momentum before and after in the horizontal direction should be same, right? So
Hmm.
before in the horizontal it was 0, and now it is minus mv plus mv dash, right?
Hmm.
Therefore it should still be 0, right? So v dash is
Yeah.
equal to mv by capital M, right?
Yeah.
If he throws it at v, now we know his velocity is mv by capital M in this side. Now all you
Hmm.
have to make sure is that he falls in the lake.
Oh, so we can just use S is equal to UT.
This distance is x. You have to be a little careful, but it is not hard. Like, you have to ensure that this velocity is sufficient for him to cover this x distance by the time he falls down, right?
Hmm.
So first you have to find out the time taken in which he will fall down to the ground, right?
Yeah.
And you should not make any careless mistake. He is right now not starting from zero velocity, right?
Oh, yeah.
He has already been falling.
Yeah. It's fallen H minus H.
Huh. So it's not going to be the same as if you started from zero.
Yeah.
So the way to find this time is basically think of this as if he started falling from capital H, what would have been the total time? Root 2 capital H by G, right?
Hmm.
And if he started falling from here to here, right?
Yeah.
What would have been the total time? That would have been root 2 small h by G, right?
Hmm.
So 1 second. Uh, so the this time is the difference of that. No.
No, but uh, I mean, the second one is for which if the initial velocity was zero, right? So,
So actually just do it. Like,
okay.
find the time it takes to fall h minus. Oh, it's very obvious. Root 2 h minus h by G, no? That is the time it takes to fall this much,
Oh, yeah.
right? He started from 0 here, right?
Okay, yeah,
And he
that's true.
went down by a distance of h minus h, right?
Hmm.
Oh, now it is obvious because now total time to fall would have been root 2 capital H by G
Okay, we
and
can subtract
subtract this
this.
time, right?
Yeah.
So real time that matters is root 2 H by G minus root 2 H minus H by G,
Hmm.
right? This is the time to fall.
Yeah.
Multiply
Okay.
it by m small v by capital M should be equal to x,
Oh, okay.
right?
Yeah.
Then he will land in the lake if this is equal to x, right?
Hmm.
If it is
Yeah.
greater than equal to x, basically he's safe, right?
Yeah.
So you can
Okay.
find your v or whatever is needed then, right?
Okay. Yeah. I guess it wasn't that hard.
Yeah.
Okay.
Then
Um, yeah. 21.
Light in certain cases may be considered as a stream of particles called photons. Each photon has a linear momentum of h by lambda. H is the Planck's constant, lambda is the wavelength. A beam of light of wavelength lambda is incident on a plane mirror at an angle theta. Calculate the change in linear momentum as the beam is reflected. Okay. So theta, and it is carrying linear momentum of h by lambda. That has been said in the question that light has each photon has this much linear momentum. So obviously it will be reflected like this, right?
Yeah.
Now change in linear momentum. Uh, find the change in linear momentum. So if it gets reflected like this, you will notice that this portion of the linear momentum has been reversed, right?
Yeah.
So h by lambda cos theta has become minus h by lambda cos theta, right?
Hmm.
It's the
Yeah.
same lambda, same light is being reflected, so lambda hasn't changed. So momentum in this case is still the same. It's just that it is in the different direction.
Okay.
So 2h by lambda cos theta should be the change, right? It is minus h by lambda cos theta right now, and later it is h by lambda cos theta upward, right?
Yeah.
This
But
component is
I,
unchanged.
yeah.
Linear momentum has two components. It's a vector. One component is unchanged. One component has been reversed,
Oh,
right?
okay. I think I misunderstood it.
Uh, what have you misunderstood? Tell me.
Like when it said, I mean, I thought that we had to find the velocity from the linear momentum somehow, and then
If you have already been given momentum, then you don't need to find velocity, no? The question is asking for change in linear momentum.
okay, yeah.
So momentum has a component, basically p, this is theta, so p cos theta and p sine theta. If it reflects, it will reflect according to the law of reflection, where this angle will also be theta, right?
Okay.
So p will come out like this because wavelength has not changed, it's the same light, right? So
Okay, yeah.
p cos theta will be this side now, and p sine theta will be this side. Basically, p sine theta has been unchanged, and p cos theta negative has become this side, right?
Okay.
2p cos theta is the change. So p is h by lambda,
Oh,
right?
yeah.
Okay.
24.
24. Okay, two persons of mass m are standing at the two extremes of a railroad car of mass capital M, result on a smooth
Wait,
track.
uh, that's not the question that's in my book. It's
Which
the
question?
hailstone one.
Oh wait,
During a
24
heavy
is,
rain.
okay, okay. I was reading 28.
Oh,
During a heavy rain, hailstones of average size 1 centimeter in diameter. Okay. Hailstone of average size 1 centimeter. Size 1 centimeter diameter. Diameter is 1 centimeter. Hailstones. Okay. Are falling at an average speed of 20 meter per second. Velocity is 20 meter per second. And suppose 2000 hailstones strike every square meter of a 10 cross 10 roof perpendicularly in 1 second. Hailstones do not rebound. Calculate average force exerted by the following hailstones on the roof. Okay. Density of the density of the hailstones is 900 kg per meter cube, and 2000 strike 2000 hailstones strike every square meter, right,
yeah.
of a 10 meter cross 10 meter roof, 100-meter square, right?
Yeah.
Number of hailstones that strike are 2000 into 100, right? Right.
Oh, okay. Yeah. Okay, I got my mistake already, I think.
2 into 10 power 5 hailstones are striking, right?
Yeah.
Total number of hailstones, and each hailstone will have some momentum. This data is going to help you find momentum, right?
Hmm.
So density diameter is this. So radius is half centimeter. So volume is 4 by 3 pi r cube. Radius is half, so half. So 1 by 8 into centimeter cube is 10 power minus 6 meter cube, right?
Yeah.
Volume into density will be mass, so 900, and mass into velocity will be momentum, right?
Hmm.
Right. So this will be the momentum of each hailstone, correct?
Yeah. That's
So
correct.
you get 2 here, you get 10 here, you get 300 here. So you get 3, this is 1000, so 1000 goes from here, and this becomes 10 minus 3,
Okay.
and 3 pi into 10 power minus 3 is the momentum due to one hailstone, right?
Okay. Yeah.
And there are so many of them, right?
Hmm.
This is initial momentum, final momentum is 0, right? They do not rebound.
Okay. Yeah.
Change in momentum is equal to 3 pi into 10 power minus 3 due to each of them, right?
Hmm.
And this is happening over a period of how much time? This happens in
One.
1 second.
Yeah.
So change in momentum by change in time is average force, right?
Okay.
dp by dt is force, right?
Hmm.
So this is force. This is average force due to one hailstone.
Yeah.
There are 2 into, so 6 pi into 10 power 2 is the average force total, right?
Yeah.
So 6 pi is 6 into 3.14, so 18.84. So 18.8 into 10 square. So almost like 18,840 Newton, right? Correct.
Yeah. Okay.
That is the average force that is exerted.
Okay. Okay. When they
24.
said average force, I thought that they meant like pressure.
Okay, I have made a mistake. It is 10 square is just 1880, right?
Yeah.
Hmm. Average force is, why will they mean pressure? Force is different. Pressure is
Yeah.
force per unit area.
Yeah. I misunderstood.
Total number, force is rate of change of momentum. So it is average force is total change in momentum by total time. And total change in momentum here is due to hailstones coming with speed and becoming zero speed, right?
Yeah.
That is the change in momentum.
Okay.
Okay, then
Yeah. 29.
28 you got.
Yeah, I got
28.
it. Like I had it tried a few times, but I got it.
I mean, make sure that you understand it properly. Like it
Yeah.
should be understood also properly. Okay, 29 then. There is a small block of mass m which is started with a speed v on the horizontal part of the bigger block of mass capital M on the horizontal floor. Uh, there is a vertical section like this, something like this. Small block of mass m started with a velocity v on the horizontal part, and it is coming like this. It is semicircular, that curved portion. All the surfaces are frictionless. Find the speed of the bigger block when the smaller block reaches point A of the surface. Okay, point A is here, and this is a perfect semicircle. Speed of the bigger block of mass capital M, right?
Mm.
This is mass capital M, the bigger block. Okay. Question is find the speed of the bigger block. when this reaches this point. Okay, fine. So you have to use conservation of energy and momentum together. So think about it right now. Try it. I'll be
Okay.
back in 2-3 minutes. Just
Yeah.
try it. Hello?
Yeah, I got it. It wasn't that hard. I
How?
think I
Hmm?
misunderstood the question like the first time.
How did you get? Tell me.
I said that momentum will be conserved in the x direction,
Hmm.
and then the initial momentum is mv, like
Hmm.
minus mv because it's in the left side.
Hmm.
And then when it gets to the point A, it doesn't have
Horizontal.
any, yeah, it doesn't have any like horizontal velocity.
Hmm.
So the total mass will have a velocity like towards the left.
Hmm.
So that'll be equal to the initial
Hmm.
momentum. Yeah, that's it.
That is the answer, na?
Yeah,
Okay. What is next?
38.
Okay. You should try 33 and all also. Okay.
Yeah, I
33
tried.
you understood, no?
Yeah, I got.
38. Two friends are sitting on a frictionless platform some distance d apart. Okay. Uh, some distance d apart. Rolls a ball of mass 4 kg on the platform towards B, which B catches, and B rolls it towards A, and they do it like that. The ball keeps on moving back and forth. The ball has a fixed speed of 5 meters per second. Okay. There is a horizontal platform. A is here, and B is here. B is here, and these have masses 40 kg and 40 kg. And then 4 kg ball is being rolled from A, and speed of A after he rolls. Okay, so basically they are not at the end of the platform, they're obviously in the middle
Yeah.
after he rolls the ball for the first time. So fine, so they are here, let's say, and here B. They're at a distance d apart, and the ball is being sent.
Yeah.
Mass 4 kg, and this is 5 meter per second, right?
Hmm.
Okay. Find the speed of B after he rolls the ball for the first time. Everything is frictionless. Yeah, fine. So, okay, so if you think of just this as a system, A plus ball,
Hmm.
before rolling, it was zero, right? Horizontal momentum.
Yeah.
So part A is just 0 is equal to 4 into 5 plus 40 into V dash, right?
Yeah.
So V dash will become minus half.
Yeah.
So basically A will start moving at minus half meter per second after first roll, right?
Yeah.
Okay. Then part 2 is find the speed of A after he catches the ball for the first time, right?
Yeah.
So first this ball will go here, and this person catches it, then this person throws it, right?
Hmm.
And in that time A is constantly moving at minus half like this, right?
Yeah.
But now the ball is coming at 5 meter per second, right?
Hmm.
4 kg ball. So now this situation, this is the initial system now,
Yeah.
and eventually A plus ball, what is the speed, right?
Hmm.
That is what is being asked after he catches, right?
Yeah.
So minus half into 40 plus minus 5 into 4 should be equal to 44 into V double dash, right?
Okay. Yeah.
This is the initial momentum, and this is the final momentum, right?
Hmm.
This is minus 20 by 44 is equal to V double dash, right?
Yeah.
So minus 40 by 44. So 10 by 11 meter per second is V double dash, right?
Okay. Yeah.
This is part 2. Now, then speed of A and B after the ball has made 5 round trips and is held by A, right? So after one round trip, speed of A was this, right? Correct.
Yeah.
Speed of A after one round trip we know, right?
Yeah.
So in one round trip, you have gotten 10 by 11 of your 10 by 11 speed, right? Now, okay, speed of B at this moment was how much? So B would have acquired, so first B catches this, right? So B would have gotten 4 into 5 by 44 is the speed, right?
Yeah.
Initially, after he catches it, this is the speed of B. You understand, no? So 20 by 44, right?
Okay.
This is clear.
Not exactly. Okay.
Is it
Okay, yeah,
clear
it's just
now?
conservation of momentum only. Yeah.
4 into 5 plus 0 is equal to 44 into V dash, right?
Yeah.
So V dash is 20 by 44, right? After he catches first.
Yeah, got it.
Then he throws,
Yeah.
right? So then right now before he throws, mass ball plus B were moving at 20 by 44 this side, right? And after he throws, ball is moving at, this is the situation for the ball, right?
Yeah.
And B, we don't know what is the velocity, right?
Yeah.
So we have to find the velocity of B after he throws it, right? So then it will be initial momentum is this 44 into 20 by 44. So 20 is equal to final minus 4 into 5 plus 40 into V double dash, right? So V double dash also becomes C 40. Oh wait, 20 plus 20, 40 by 41, right? Right?
Yeah. Yeah.
This is going at 1 meter per second. And after A catches it, he was going at 10 by 11, right? 10 by 11 meter per second. Correct?
Yeah.
Now the same experiment is repeated, right? This is one round trip. Second round trip, you do the same calculations, right?
Yeah.
So one more round trip, we need to see the pattern, right? Then we'll get a pattern, and then 5 round trips we can find, right? So
Yeah.
let's do one more round trip, and then we'll be able to guess.
Okay.
So 1 second. Let's check the answer first. This is correct, no? First part A and part B.
Okay.
Which
Yeah.
question
Correct.
number it is?
38.
Okay, so this is correct. Then we can try and do the rest.
Yeah.
Okay, so right now A is going at 10 by 11 with the ball, right? And again, he will send it, right?
Yeah.
So he will send it and finally he will catch it again, right?
Yeah.
Okay. Fine. So 10 by 11 into 44 negative should be equal to 4 into 5 plus 40 into V this, right? After he throws the ball, right?
Okay. Yeah.
So this is minus 40 minus 20 minus 60 by 40 is equal to V this, right? So minus 3 by 2, right?
Yeah.
This is the velocity of A after he throws the ball. Then later ball is coming back and he is going at 3 by 2, right?
Yeah.
Ball is coming at 5, right? So then final velocity will be 3 by 2 into 40 plus 3 by 2 into 40 is equal to, no, plus 4 into 5
But shouldn't it? Okay.
is equal to 44 into V, right?
Wait a okay. Yeah.
Final velocity will be this one. No? This is initial, just before he catches it is this. Just after he catches it is this, right?
Yeah.
So this is 20, 60 plus 20, 80 by 44, right? which is basically 20 by 11, right? So we get the pattern basically, right?
Okay.
After
Yeah.
2 round trips, the velocity is 20 by 11. After one
Hmm.
round trip, it was 10 by 11. So after
Okay.
5 round trips, it should be 50 by 11,
Yeah.
right? And similarly for A or B also you can say. So B, after the ball is coming now, let's say at 5, and he catches it, right?
Hmm.
So 4 into 5 plus 40 into 1 is equal to 44 into V, right? So 20
Yeah.
plus 40, 60 by 44 is the V when he has held the ball, and then he has to throw the ball back, right?
Hmm.
So let's find that. So initial momentum is 60 by 44 into 44 is equal to 40 into V minus 20, right?
Yeah.
So this becomes 60 plus 40, 80 by 42, right?
Hmm.
2 meter per second after second round trip. So this is moving at 5 meter per second now, right? After five
Yeah.
round trips, right? So after 5 round trips, B is moving at 5 and A is moving at 50 by 11 in this side, right?
Yeah.
After that, no more balls can be sent. No, because when the ball is sent at 5, it will never reach him.
Oh, okay. Yeah.
5 is the maximum number of round trips, right?
Yeah.
Because ball cannot reach him because B is already far off and he's moving at the same space, right?
Hmm. Okay. Yeah.
So that is the final round trip basically, right?
Hmm.
So how many times can A roll the ball, right?
Okay. So that's 5.
Uh, that will be 5 only. After that, he cannot roll. If
Yeah.
he rolls it, it will not come back.
Yeah.
Can roll it once more, but 6 obviously,
Okay. Yeah.
right? He can roll it once more, but it will not return, right?
Hmm. Yeah.
And where is the center of mass of A plus B plus ball at the end of the nth trip, right?
Hmm.
Where is the center of mass of the system A plus B plus ball at the end of the nth trip? Okay, so A plus B plus ball system, there was no external force.
Wait, the nth trip meaning like nth round trip, right?
Whatever, doesn't even matter.
Okay.
Why? Because A plus B plus ball is the entire thing, no?
Hmm.
What is there? Nothing else is left, right?
Okay. Yeah.
This is the entire system. There was no force on the system, no?
Yeah.
External force, right? So
Hmm.
center of mass will be wherever it was in the beginning, right?
Yeah.
That cannot change, no?
Hmm.
So they were separated by D, and who was holding the ball in the beginning?
A.
A was holding it. Yeah, rolls the ball, huh? Right?
Yeah.
So where is the center of mass? It is with this 44 and this is 40, and it is at a distance of 44 into 0 plus 40 into D by 84, right? From here, right?
Hmm.
Initial center of mass distance will be this, right? From A
Yeah.
side, right? So it is 10 by 421, right?
Yeah.
10D by 21 from A, right?
Yeah.
This is the initial position of center of mass. This cannot change because you have taken the whole thing as a system. There is no external
Hmm.
force on it, right?
Yeah.
If you had taken A plus ball as a system, then that obviously there is external force from B.
Yeah.
That B applies forces on ball, right?
Hmm. Yeah.
Then it would be different, but this whole thing is going to remain at this position only, right?
Yeah.
So 38 last answer will be 10D by 21 away from initial position of A towards B,
Yeah.
right?
Yeah.
Okay.
Okay. Got
What else?
it. Yeah. 40.
Which one?
40.
Okay. In a gamma decay process, the internal energy of a nucleus of mass m decreases. Okay. Gamma decay process. Internal energy of a nucleus of mass m decreases. A gamma photon of energy this and momentum this is emitted and the nucleus recoils, right? Find
Hmm.
the decrease in internal energy. Okay. So suppose there is a nucleus of mass m. In the decay process, suddenly what happens is a gamma ray is coming out, right?
Yeah.
Gamma ray. This has this gamma ray has energy, gamma photon has energy E and linear momentum E by C. Energy E and momentum E by C, right?
Okay. Yeah.
Correct. And he's saying internal energy of a nucleus of mass m decreases. Fine. So, okay. So, by conservation of momentum, you can say that here in momentum was zero, right?
Yeah.
Here momentum is E by C on this. So, momentum of this should be E by C this side, right?
Yeah.
Right. So, momentum of mass m should be E by C, right? So, velocity of this, right?
Hmm.
Basically momentum of this nucleus has to be
Yeah.
backward E by C, no? So velocity of the nucleus is E by mc, right?
Yeah.
Correct? Makes
Yeah.
sense. So okay, so
Hmm.
kinetic energy of the nucleus is what? Kinetic energy of the nucleus is half into m into E square by m square c square, right?
Yeah.
E square by 2mc square, right?
Hmm.
Correct.
Okay.
So
Yeah.
this is kinetic energy final for the nucleus, right?
Hmm.
And energy of the photon was E, right?
Yeah.
Correct. So total energy final, total energy is E plus E square by 2mc square, right? So of the system.
Hmm.
Uh,
But
you have to find what? You have to find
the
change in
decrease in.
internal energy of nucleus of mass m decreases, gamma photon of this much and linear momentum this much is emitted. Nucleus recoils. Find the decrease in internal energy. Decrease in the internal energy. Okay, that means you have to find some way of finding the initial internal energy.
Yeah.
So okay, let's say this was E naught, initial
Okay.
internal energy, and you should have, by conservation of energy, you should have E naught should be equal to ke plus E, right?
Yeah.
Plus E final, right? This is E naught is initial internal energy,
Okay.
E final is E final internal energy, right?
Hmm. Yeah, and
See,
it loses some.
E final is this final internal energy, right? So you should have total
Okay.
initial
Yeah.
energy should be equal to kinetic energy plus energy of the photon plus E final, right?
Yeah.
No other energy is there, no anywhere else now. Correct?
Yeah. No.
So E naught minus EF is the change in internal energy, right? Is equal to kinetic energy plus
Hmm.
E, right? Correct?
Yeah.
So
Yeah.
kinetic energy plus E, kinetic energy we have already found out, right? This is the change in
Hmm.
internal, this is negative of the change in internal energy, right?
Hmm.
So decrease is basically this much. So E plus E square, that should be the answer. This is the change in internal energy.
Okay.
You understand?
Yeah.
Basically, the only things you can do is momentum conservation and energy conservation, right?
Yeah.
It's not like anything else is possible also.
Hmm.
So momentum conservation gives us the velocity, right?
Yeah.
Because this momentum is coming out of nowhere, so this must also have this much momentum, right? Backward.
Yeah.
So velocity must be E by mc, so kinetic energy must be this much, right?
Hmm.
And
Yeah.
then think about, let's say internal energy is E naught here, let's say internal energy is EF here. So conservation of energy tells that E naught should be equal to EF plus kinetic energy nu that has been acquired and energy of the photon, right?
Yeah.
So you get E naught minus EF is this. That is the answer.
Okay.
Okay.
Yeah.
So energy conservation, momentum conservation are going to tell you things like which you would not have been able to get if you were relying only on Newton's laws, right?
Yeah.
Here, it is not possible to solve this question by Newton's laws and all. You don't know the forces,
Hmm.
right?
Yeah.
So, okay, what else?
Uh, 44 and 45. They're kind of like the same question.
Okay, 44. A ball falls on an inclined plane, makes a perfectly elastic collision. Okay, when will it hit the plane again? Ball falls from a height h. Okay, h above the point of impact, right? So, what is the velocity just before hitting here? Root 2 gh,
Yeah.
right?
Yeah.
Then this is the normal, and if this is theta, this is 90 minus theta. So
Hmm.
this is 90, so this is theta, right?
Yeah.
So velocity was in this direction. So this is 90 minus theta. So this is theta, right? Correct?
Yeah.
So V cos theta is in this direction and V sine theta is in this direction, right?
Hmm.
Correct. V was equal to root 2 gh.
Yeah.
Okay. So now he has given coefficient of restitution, right? No, he has not given. It is perfectly elastic, he has said, right?
Yeah.
In this case, it is perfectly elastic. Okay. So in perfectly elastic collisions, we know velocity of separation is equal to velocity of approach, right?
Yeah.
Velocity of approach for perfectly elastic, right?
Hmm.
However, here this is like an oblique collision, right? In the
Yeah.
sense that you are not colliding head on, right?
Yeah.
You are colliding at an angle. So what matters is the head on part, right?
Yeah.
So because what happens is when it hits, the force that is exerted on the block will be a normal force in this direction, right?
Hmm. Yeah.
So the normal force is the force that is acting for a
Yeah.
brief moment of time. So the change in momentum will only be in this direction, right?
Okay. Yeah.
So this direction is untouched, okay?
Hmm.
Because there's no force on that direction, right?
Yeah.
So the all the laws of this coefficient of restitution stuff will matter only for this particular direction, right?
Yeah.
So it's almost as if you had thrown the ball along the normal at v cos theta rather than thrown it like this, right?
Okay. Yeah.
So because velocity of separation is equal to velocity of approach for an elastic collision, after collision it will bounce back with a v cos theta, right?
Hmm.
Correct, because it was hitting with a v cos theta, right?
Yeah.
So in
But
the second
okay. Yeah.
question, in 45 question, it will bounce back with e v cos theta,
Yeah.
because then there will be a coefficient of restitution, right? Which is not
Hmm.
1 in the second question, correct?
Okay. Yeah.
But v sine theta remains unchanged.
Yeah.
So the situation is now the final velocities are these, right?
Hmm.
Correct. So
Yeah.
v cos theta and v sine theta. And now the question is basically if you have a body that is going at v cos theta like this and v sine theta like this, where will it fall on the incline, right? Correct.
Hmm.
So during any
Yeah.
portion of its motion, uh, mg will be like this, mg will be like this, and mg sine theta will be like this, and mg cos theta will be like this, right?
Yeah.
Correct. This is the component of the mg force, right?
Yeah.
So uh, so that means that acceleration down the incline is g sine theta and acceleration like this is g cos theta, right? For the
Hmm.
particle, right? Correct.
Yeah.
So this is a projectile motion question, but the differences are these. Velocity vertical is v cos theta, velocity horizontal is v sin theta, and downward gravity, see, this is what is bringing it back to the plane, no? Downward gravity is g cos theta, but there is a forward gravity also g sin theta, right?
Yeah.
You understand? You can just twist yourself and look from here, right? This is the same projectile motion graph that I have drawn,
Yeah.
right? You can stand here on the incline and see the, instead of g you have g cos theta, and there is a forward g sin theta which was not there in normal projectile motion, right?
Yeah.
So that is the only difference. So time of flight will be very easy. Time of flight will be 2 v cos theta by g cos theta, right?
Yeah.
2 vertical component by g cos theta, right? So that will be simply 2v by g, right?
Yeah.
Time of flight. So distance traveled in this much time would be s is equal to ut, so v sin theta into t, t is 2v by g, plus half a is g sin theta, t square is 2v by g whole square, so 4v square by g square, right?
Yeah.
Correct. So this g 2 2 2v square by g sin theta and 2v square by g sin theta, so 4v square by g
Yeah.
sin theta is the distance it travels on the incline before it
Okay.
hits. Okay.
Yeah.
So question 44 should be 4v square by g sin theta. Okay. Now we know that v square is 2gh, right? So 4v
Oh
square
yeah.
by g sin theta will become what? 4 into 2gh. So 8h sin theta,
Yeah. Okay.
right?
Yeah.
So that is the answer, 8h sin theta along the incline. In the next question, the only difference is that it comes up with EV cos theta, right? EV cos theta, so time of flight will become 2 EV cos theta by G cos
Yeah.
theta, right? So 2 EV by G and stuff, right? And everything is same. So just put all the values, you'll get the answer.
Okay.
You understand what happened?
Yeah.
Why did we do the components of velocity? Because only the head-on component, only the vertically perpendicular component of velocity will change, right? The
Yeah.
horizontal component of velocity, which was along the incline, does not change during collision because there is no force in that direction, right?
Yeah.
Normal force is what is causing the change in momentum. So only v cos theta component changes. And in this case, it is elastic collision, so it doesn't even change. It just
Yeah.
reverses direction. Correct? In a non-elastic
Yeah.
collision, you will have E component which will come in and it will be EV cos theta and stuff. After that, it is projectile motion on an inclined plane, which should be understandable, right? That you know how to do, right?
Yeah. Kind of.
The second part, is it a problem? How far it will go down and all?
No, the
Kind
second
of
part
is
is
not
the same.
inspiring confidence. Second part is not, should not be a problem. No, if you know this and this.
Yeah.
Are you sure you know it, or are you not saying just for the sake of it?
I mean, I'm not that good at projectile motion, but I mean, I got the concept for this question.
You cannot uh, you cannot do it question by question. Okay, it's not like this question I understand but generally I don't understand, right? That
Yeah.
way is not the right way to do anything. So how will you find, suppose I launch this with an angle of 45 degree and here this 30 degree, how far it will go on the high incline?
Okay, I'll try. Wait, so I should find the range, right?
Cannot use formulas in this.
Yeah.
Don't try to use formulas.
Okay.
It will not help. So you have to understand what is going on. So what is the, think of the inclined plane and see the velocity components, right? V cos 45 in this direction, right? And V sine 45 in this direction.
Yeah.
Now this is the initial velocities. While it is in motion, at any point gravity is vertically downwards, right?
Yeah.
So G should be vertically downward, but because of this inclined plane, I can say G, suppose this is 30, then this is 60, right?
Mm.
So G has two components. One is along the incline like this, G cos 60, right?
Yeah.
And one is G sine 60 like this, right?
Mm.
Perpendicular to the incline, right?
Yeah.
So so there is one component like this and one component like this for the gravity force, right?
Mm.
So now this is the same question as a typical normal projectile motion. In a normal projectile motion, you launch something, you have one component, this is G, and this component is 0, right?
Yeah.
In this case, when you have launched it, look at it from this perspective. Look at it like this, right?
Mm.
You have a downward component and a backward component also, which is not 0,
Yeah.
right? So first I have to find time of flight. No, which component is making it fall to the plane? This is the component, no?
Yeah.
So this component G sine theta is causing it to come down, right?
Mm.
So time of flight will be G sine theta is replacing your G, right?
Yeah.
So time of flight will be just V sine 45 by G sine theta into 2, right?
Mm.
V sine 45 degree by G sine theta into 2 will be the time of flight total, because it will reduce it to 0 in this much time, G sine V sine 45 by G sine theta, right?
Yeah.
And then double of that, right?
Mm.
This is time of flight, and then distance covered will depend on initial velocity and acceleration, right?
Yeah.
S is equal to, initial velocity is V cos 45 into time of flight. Time of flight is this thing, 2V sine
Mm.
45 by G sine theta, but this time acceleration is backward, it is G cos 60, right?
Mm.
Minus half into G cos 60 into this time of flight square. So 4V square cos square 45 by G square sine square theta. That is the distance covered.
Yeah.
You should solve chapter 3 questions, inclined projectile questions from your Allen book or from HCV.
Okay.
Make sure that you understand it. This is not hard. You have to do Y component separately and X component separately. And in
Okay.
this case, you have to put your X and Y axis instead of normal X and Y axis like this, Y and X. It
Mm.
is more convenient if you think of it like this,
Yeah.
Y and X. So G has two components, and that is the only change. After that, it is a regular projectile motion,
Mm.
right?
Yeah.
But you cannot use any formulas because range formula assumed that there was no horizontal component.
Yeah.
You cannot use those formulas and all.
Okay.
You can only use time of flight with a different G. Time of flight used to be 2V sine theta by G, where V
Mm.
sine theta was vertical component, but G is now not G, it is G cos theta.
Yeah.
Right? So time of flight you can possibly use using the formulas, but obviously range is different because there is an acceleration,
Mm.
right?
Yeah.
Okay. Continue chapter 8 exercises, and this exercise is whatever is left, right?
Yeah.
Chapter 8, you should try what 64 questions are there. You should try as much as you can.
Okay.
We will discuss this and hopefully we'll finish it in the next class. The last two, both the exercises complete thing. Okay.
Okay.
Okay. That's
Yeah.
all for now then.
Okay. Thank you.
Okay. Bye.
Yeah.